Okay, so here we see the title, A Logical Interpretation of Asynchronous Multiparty Compatibility, and Sonia will give the talk.
Hi, thank you. So this is joint work with Marco Carbone, who's in the room, and Carsten Schürmann. And yes, it's about a logical interpretation of asynchronous multiparty compatibility. So the background for this talk is the Carey-Howard correspondence between the lambda calculus and intuitionistic logic, which has served as inspiration for many, many works. And it's been shown that there is a similar correspondence between session-typed bicalculus and linear logic. And we believe that by exploring this correspondence more deeply, it could also become a fruitful inspiration source. Sorry for my voice. So this correspondence between the session-type bicalculus and linear logic, I'm going to give you a bit more details. But it's basically established for a restricted part of this bicalculus. And so the main concept that we were interested to understand within that correspondence is the one of multiparty compatibility, as you saw in the title. So what is multiparty compatibility? It's a concept that has emerged in the multiparty session type community. So it's intuitively the fact that given a set of processes, they can communicate without reaching an error. You can put them together and they will live happily ever after. So it has been conceptualized by different authors in different ways. But what comes back as kind of the main idea is the fact that the computation path is live, meaning that every input message is eventually sent and every sending instruction is eventually executed. So nobody gets stuck with a message that needs to be sent and is not, or something that is sent and that is not received. So as I said, there are different formulations of this concept of multiparty compatibility, but they are usually based on the semantics of the processes. So you give the processes some understanding, some formal understanding of their behavior, and depending on how these behaviors compose, they will be said to be compatible or not compatible. So because we are working in this context of the Carey-Howard correspondence, we want to work in a very syntactic way. So what I will present today is a syntactic understanding, and in fact a logical understanding of this multiparty compatibility. So let me go back on the Carey-Howard correspondence for session types. So I'm not going to give any formal definitions, but I'll mostly base my talk on examples. Session types are a way to give types to processes, communicating processes. So binary session types processes that communicate, that two processes that communicate. So for example, here I have process P1, which sends something, then receives something and closes, and P2, which receives something, sends something and wait. And of course the idea is that P1 will send this something which, I had animations which I forgot. So let me go back. So P1 sends something and wants to receive something. P2 receives something, wants to receive something and to send something. And so, yes, so the idea is that it is possible to see the typing discipline on these processes in correspondence with linear logic. So we use linear logic's connective as a result to read these types. So okay, maybe I can I point? No. Okay, maybe I cannot point. So the cross circle symbol is called a tensor, and it's used to type sending operations, and the reverse ampersand is called par, and is used to type sorry, is used to type receive operations. So because so if we say that this little variable a was of type A and little variable b was of type b, again I cannot point and I cannot move from the mic. So we have some basic types A and B, and these are the types of the things that are sent and received. And these two types corresponds to the messages, sorry, the processes that are on the left. I hope it's clear without the pointing. Right. So the tensor corresponds to outputs, and the par corresponds to inputs. So, and the reason why we can say it's similar to Curry-Howard correspondence is because a proof in linear logic of this type will really correspond to a typing inference for the corresponding process. So by reading bottom up, we want to type this process. Okay, the image doesn't correspond. P1, yeah, it's P2. It should be P2. It should say P2 there. So so the reception is this par operator, and then we can apply this rule, this par rule. Then the send corresponds to the tensor operator, which corresponds exactly to the tensor rule in linear logic, and so on. So the correspondence is not just the fact that the types can be written in this language, but it really is at the level of the proofs and type inferences as well. And then, similarly to the Curry-Howard correspondence, sorry, similarly to the Curry-Howard correspondence for lambda calculus and linear logic, the correspondence goes one level deeper, which is that so in lambda calculus, it's the fact that the lambda reduction can be seen as cut normalization in intuitionistic logic. And here we have the fact that when we put these processes and have them communicate with each other, we can see this also as the cut rule, the cut reduction rule in the linear logic. So this was all previous work. So one thing to notice is that, okay, this is kind of a simple notion of compatibility. Here we have that these two processes, they can communicate because every send action is matched by a receive action, which is transferred to the type level by the fact that the two types are dual to each other. So tensor is dual to par, and so when we have a tensor something, or a tensor, the rest of the formula, and a perpendicular par, the rest of the formula, these two types are dual, and therefore the process can communicate. So it goes both ways. If the two types are dual, they can communicate. Right. So it is one simple case of compatibility. So this case of compatibility is the case where we are in the binary setting and the communication is synchronous, meaning that every send is happening exactly right at the same time as the receive. We can do it at the same time if we want. So again, as you saw in the title, the idea of this work is to generalize this to multi-party compatibility. And so multi-party means that we want more than two processes to communicate together. This has been studied a lot in the multi-party session, in the session type community by multi-party session types. And it has also been studied in the context of this Curry-Howard correspondence. So I will give you a bit more details on that now. Okay, so all the things that I said before about using linear logic for each single process works. The only question is, how do we compose them together? Because now clearly they are not dual to each other. The first process sends an A, receives a C. The second one receives an A, sends a B. And the last one sends a B, receives a B, sends a C. So they are using different types to communicate. But it's still clear that they can communicate with each other, that they are compatible. So you need to extend this notion of duality on types to something more that can account for this. So the concept that has been introduced by Marco and others is the one of coherence. So what does coherence do? Well, it does what you expect. It kind of matches it kind of does duality, but not throughout the formula, but bit by bit. So it just looks at the beginning of the formula, looks at it is dual, and continues. So before, when we were looking at dual types and in the binary setting, really the whole formula was dual. A tensor B power 1 is really dual to A power B tensor 1. Whereas here we have this bits by bits duality. So we have, again, looking bottom up, we are removing one bit of the duality each time. So that is a condition that is sufficient to show compatibility of these two types and therefore of these processes. But as you can maybe see, that it kind of imposes this this fixed timeline, right? This fact that first we have to match the A's and then we have to match the B's, and so now we want to have a way to extend this, because these are not the only processes that are compatible. So now let me get into the other kind of axis of this generalization, is to look at processes that where we cannot do this matching in bit by bit. So namely, the communication has to be asynchronous. So if we have two processes, one sends an A, waits to receive a B, and another one sends a B and wants to receive an A, well, they can still communicate, because they could send whatever their message was in the network, and they could then receive what they were waiting to receive. But none of our preceding criteria was applicable here. So we can still give them linear types in a similar way. So tensor is still used to describe send, and par is still used to describe receive. But clearly, the two types now are not dual anymore. So we need again a way to show that these types are compatible. And so that means a syntactic criterion on these types that make them that shows that they are compatible. So the idea is exactly like I described informally, which is that instead of doing the communication immediately, you can store the message that is sent in a buffer to wait at a later time to be received. So we add these kind of stacks at the front of each formula, of each type, to represent that fact that there is something that has been sent but hasn't yet been received. So then the two send operations can be done, and then the two receives operations can be done, and that's it. The processes are compatible. So our work is therefore here in this last corner. So we have a syntactic characterization of compatibility in the context of multi-party sessions and asynchronous communication. So again, we are in the same context where we can represent the types by these linear propositions, and all these processes want to send at the same time, and they want to receive afterwards. And so our criteria will be on these three types, a way to show that they are compatible, and therefore we can execute the communication in a correct way without reaching an error. Okay, so how does it work technically? Here we will again use buffers, but we need a bit more information in the judgment, in the type judgment, to be able to execute the communication correctly. And what it means is that each type here needs to be labeled by the receiver or the sender of the information. So here we have three operations. Okay, and one thing that is maybe a bit confusing is that we now have to flip all the types to their duals. Yeah, I didn't want to write something incorrect, but maybe I should have so that it would be clearer. So basically, we need to say that X1, process 1, which type B1, wants to send to a specific receiver. So we want the par symbol to be labeled by X2 because that's who is going to receive, who is expected to receive A. And same for X2 is sending this B to 3, and 3 is sending the C to 1. So we need to indicate that in the judgment to be able to then, when we look again in the premise, to be able to have the buffers also labeled by the correct receivers. So each operator of the language is labeled by who is going to receive or who is going to send, and the buffers are also labeled. So that means that, again, all the send operations can happen at the same time, the buffering can happen in parallel, and then the receiving operations can be staged in order to, and again, because there could be conflict in who is going to receive what, we want each operator, also the tensor operator, to be equally labeled by whom the message has been sent. So we want always to indicate the message has to be sent to that person, that process, and I want to receive this message of this type from that process. Because here I took an easy example where A, B, and C were different, but if you imagine that A, B, and C are the same type, then you also want to say, I'm waiting for something of type A from that specific process. So I want all of this information to be recorded in my judgment to be able to then say these types are compatible. Okay, and that's kind of what asynchronous forwarders are. So the forwarders are these objects that that ensure that that these processes are satisfying these syntactic criteria. And so these asynchronous forwarders characterize exactly the types that are multi-compatible in the sense that I introduced at the beginning. That is the semantic notion that was in the literature, in the multi-party session types literature for a long time. And so we have achieved that goal to give a logical characterization of this notion that extends the Curry-Howard correspondence between the session type bicalculus and linear logic to this wider range of processes. And on top of that, these objects that are forwarders that are computing this compatibility notion, they're also they can also be made to communicate together. So that's an extra step that I don't have time to explain now. Okay, I think I'll stop here. Thank you very much.
So, are there any questions? Yep.
Hi, Sonia. Thanks for the presentation. I'm sorry, I have to keep you talking. I didn't really understand how you pick the labels when you're doing the forwarders. Can you go back a couple of slides? When you pick the X1, the X2, how do you know that you're picking correctly?
Yeah, so they are, okay, maybe let's go back here.
Yes, exactly.
Yeah, so the process 1 sends A to process 2. Yeah, exactly. I mean, basically you pick the labels in the way that will enforce what you want to observe, yeah.
So maybe I have a question. So with this result, how can you apply it? So do you have a particular language in mind or set of setup where you can use it? Or so what is the advantage that you know this precise characterization of multi-party types?
So I don't, because I'm a theorist, but maybe I can ask my co-author. Do you want to say something?
Well, I guess
you need the microphone.
I guess that you can use this you have a set of processes, and usually this notion of compatibility is, in general, you don't have, if you want an algorithm for checking if these things are compatible, so you could use this as an algorithm. The problem is that what is missing here is that you don't have infinite processes. So and things become harder when you do that. So I believe that the next step here would be to understand actually how to extend this to infinite processes.
So if there are no more questions, so thanks again for the presentation and for the discussion.